Thank you everyone for attending. Today I'll be presenting my thesis defense on advancing multimodal sensing and robotic interfaces for chronic care. So chronic conditions are long-term health issues, often with no cure. They can impair basic functions like mobility, self-care, and other activities of daily living, significantly reducing independence and quality of life. They can also have changing symptoms over time, making them challenging to track and treat. There is a huge shortage of tools that enable and empower patients to manage their chronic health conditions. So at the start of my PhD, in my first few meetings, Zachary and Carmel asked me what I wanted to work on. I knew I could only make it to graduation if I worked on something that was extremely important to me. I chose to focus on the challenges in managing chronic illnesses, challenges I faced firsthand during my own childhood and teenage years. When I was just a few months old, I was diagnosed with a dermatological condition named eczema. Eczema is characterized by dry, itchy, inflamed skin, which leads to scratching behaviors. In the photo shown, you can see me scratching and some of those itchy, inflamed patches of skin on my face. Eczema affected many aspects of my life throughout childhood. I remember constantly having disturbed sleep, bad focus, and low energy due to the continuous scratching. My parents and I tried many different treatments over the years. However, it was often hard to know what was working and not, especially with changing symptoms over time. In my second year of high school, I was faced with a similar, more severe condition called topical steroid withdrawal, caused by medications used to treat eczema. This led to a series of several years out of normal school, faced with even more debilitating versions of eczema-like symptoms, including the chronic itch, and also facing additional impacts, including depression and extreme fatigue. Navigating the treatment decisions, including medications, creams, light therapy, and alternative medicine approaches, was even more challenging during this time for my parents, doctors, and I. There was a huge lack of data to know how my symptoms were progressing and what was affecting them. The only data point we had came from blood tests, for example, shown here, which is an IgE antibodies test, which showed significant inflammation in my body. However, blood tests are too intermittent to provide any utility. My experience helped me identify the first limitation in chronic care that I aim to tackle in my PhD, the lack of continuous quantitative data to inform treatment decisions for patients and clinicians. The second gap identified was the lack of personalized management and agency while suffering from a chronic condition at home. This is something I faced throughout the years of my recovery, but was especially apparent to me when I was diagnosed with a spinal bone infection, which limited my ability to use my lower body for a couple of weeks. During this period and the recovery that followed, I was fully reliant on the hospital staff and my parents, significantly limiting my feeling of control and agency to do even the simplest of tasks. These experiences motivated me to pursue multiple projects in multimodal sensing in portable form factors. In this talk, I aim to show you how multimodal sensing in portable form factors can enable continuous quantitative monitoring and personalized management for chronic conditions while empowering patients. So first of all, what is multimodal sensing? Multimodal sensing involves integrating various sensing modalities, including cameras, inertial measurement units, and contact microphones, into various devices, including Meta Ray-Ban smart glasses, a GE handheld ultrasound probe, an Oura Ring, or an Apple Watch. These are some of the portable device form factors that I used in the projects I'll discuss later in this talk. These devices already have various existing use cases. This includes fitness tracking, sleep tracking, and fall detection. However, there are various chronic health use cases that have yet to be explored using portable multimodal sensing that could really benefit patients. So developing these sensing systems for chronic health is an extremely challenging process, and this is because it requires so many steps. So you start off by identifying your problem, do some sensor and device design, you go ahead and collect some data, you go ahead and do some data processing, train some algorithms, and then you evaluate with end users. And these are just a few of those steps. In reality, these steps are not linear. They're all interconnected, which makes this even more challenging. So as an example, you can go ahead and build out your device, collect some data, do your data processing, train your ML algorithms, and then realize that your data was not good enough to begin with. So you have to go all the way back and create a new device or iterate on that. It is also important for these steps to be conducted in conjunction with medical professionals and end users to make sure that you're developing stuff that people want and will use. To summarize, this is a complex process involving technical challenges across various domains, including mechanical and electrical engineering, signal processing, and machine learning. It requires collaborating closely with medical professionals and end users. It requires designing and conducting various human studies. This involves, data collection studies and also longer-term studies in the home. And lastly, it requires iterating with multiple stages of development and refinement. So let me start with the talk overview. So in the first part of the talk, we'll be talking about multimodal sensing for dermatological conditions. In this part, I'll be talking about two projects, the first on a scratch tracking ring, and the second on a gel site probe for analysis of the skin surface. The goal of this part is to provide those quantitative measures that currently don't exist for patients and their doctors. The second part is going to be on multimodal interfaces for physically assistive robots. I'll be talking about two projects. The first, which is this head-worn interface for mobile manipulators for individuals with motor impairments. And the second is a wearable interface for bite timing estimation. The goal of the second part is to provide personalized caregiving while maintaining the feeling of control and agency for the users. So let's start with project number one, multimodal ring for tracking scratch intensity in patients with chronic itch. In this part, I'm going to show you how you can use two sensing modalities, an accelerometer and contact microphone. We can go ahead and integrate this into a portable device form factor, specifically a wearable ring, and we can use it to track chronic itch in patients, specifically for tracking scratch intensity and scratch detection. The goal, once again, is to provide those quantitative measures that currently don't exist for patients and their doctors. So as a bit of a background, chronic itch is caused by conditions such as eczema, psoriasis, and liver disease, and it affects millions of people around the world. The itch and the scratching behaviors are currently only tracked through the scales shown or through visual inspection. These scales are extremely subjective and have been shown to be extremely prone to recall bias and response shifts. This is what is currently being used in clinical trials for new eczema drugs. The lack of quantitative measures specifically presents difficulty in assessing medication and treatment efficacy, identifying itch triggers, and also understanding how itch symptoms are affecting other aspects of life, such as sleep. Providing these quantitative measures of scratch metrics through multimodal sensing would empower patients and allow them to take control of their condition. So as you may have guessed, there's some research in this space. And the first is this, what's considered ground truth is infrared and thermal imaging for tracking scratching, primarily at night. The problem with this method is it requires the person to be in front of the camera, and the data also needs to be hand labeled, which is extremely time intensive. For the two wearable methods shown, these have several limitations. One, they're trained and evaluated using data only at night. The bottom is a non-aesthetic form factor, which prevents adoption during the day. And lastly, they only provide scratch detection, so scratching versus non-scratching. While scratch detection is a useful metric, it doesn't paint the full picture of scratching behavior. For example, two patients may scratch the same amount of time per day, but one may scratch much more intensely, causing more damage to their skin. So to address these limitations, we present a multimodal sensing ring consisting of a contact microphone and an accelerometer. We then go ahead and present a framework for using a pressure-sensitive tablet for capturing ground truth scratch intensity values and training intensity estimation algorithms. And lastly, we show that this enables the quantification of variations in the patient interpretation of the 0 to 10 intensity scales that I previously showed. So to start off, this is what our prototype wearable ring looks like, and it's a tethered ring, and it consists of two sensors on the finger that provide complementary acoustomechanic features of the scratching motion. So a contact microphone is a piezoelectric element that senses vibrations through solid objects, which means it's completely unaffected by acoustic waves, thus eliminating audio and speech privacy concerns. In conjunction, these sensors capture both low-frequency finger and arm motions and the higher frequency vibrations propagating from the fingernail to the ring. Scratch intensity is important as it is the key to understanding how much damage is occurring to the skin. However, it currently doesn't exist in literature in a physical unit, so we have to go ahead and define that. So as itch increases in severity, patients often scratch with a combination of increased normal force and velocity. So we propose using mechanical power as a metric for scratch intensity, calculated by taking the product of force and velocity. However, force and velocity cannot be estimated accurately through human observation or techniques such as motion capture, and thus we use a pressure-sensitive tablet to go ahead and capture this data. So this is what it looks like from the pressure-sensitive tablet when you go ahead and scratch on it. And specifically, we use this commercially available tablet named the SensoMorph. This device allows us to automatically generate those power values, and let me show you how this works. So we have participants scratch on just one finger on the tablet, and then we go ahead and get a force map, which has the contact that was identified and the force for that contact region. From there, to get the average force for the sample of data, we simply take our force over time signal, and then we can go ahead and take the average force. In these plots shown, you see two examples. The top is where the user maintains contact with the tablet throughout the scratching motion, while the second is where they lift their finger up and down between different scratching motions. The velocity algorithm is a little bit more involved. So over here, we have our time steps and our X and Y positions over time. We can go ahead and then interpolate and then smooth and get the critical points of the signal, which are basically the start and stop of each scratching motion. That allows us to calculate distance. Then we can get distance over time to get average velocity for 1 second of data. We can go ahead and then multiply these two values to get our power in milliwatts. We went ahead and ran this data collection study with 20 participants where we instructed them to scratch on the tablet at subjective combinations of low, medium, and high force and velocity. And this is what the power labels look like for our data sets. And you can see that as the scratch intensity increases, as you'd expect, the values increase off the tablet. So let's now take a look at our pipeline. So we have our wearable device here on our participant. From there, we have our contact microphone raw data on the top and the accelerometer raw data on the bottom. We can go ahead and extract some features using the discrete Fourier transform. This is specifically frequency features, as we find that the magnitude of these are helpful for learning scratch intensity. From there, we can concatenate these and use these to train two neural networks, one for scratch intensity estimation and the other for scratch detection. So now let's talk about scratch intensity results. Specifically, we find that the multimodal algorithm has the least error for scratch intensity estimation. So now the problem comes about is how do we validate these algorithms for scratching directly on skin, as so far we are only using that pressure-sensitive tablet. So we go ahead and run this validation study with 14 participants where they wear the device, and we instruct them to scratch on their skin at various intensities and also on the tablet at various intensities. We specifically use the scale shown, which goes from 1 to 5, where 1 is the least intense scratching, which you would do on your skin, and 5 is the most intense. So what we find from this plot is that our device can successfully differentiate between 5 intensities of scratching on the skin. So on the x-axis, you see those 5 instructed intensities. On the y-axis, you see the regressed intensities off the device, and we find statistical significance between those 5 different values. If we go ahead and now look at that data coming off the tablet and compare it to the instructed intensities and fit a line for each participant, what we find is participants have vastly different scales. And so that's basically shown by each of these lines, and that shows what the participants' understanding of that subjective scale was. And so for the first time, we're able to capture these subjective variations in scratch intensity. To make that a little bit more clear, I picked 3 participants who have the most distinct scales. And if you look, the colors on this heat map basically indicate the power with what they're scratching at. So if you look at participant 3, who's the first column, their level 10 scratching is about 350 milliwatts. Well, if you look at their level 1 scratching, that's around 150 milliwatts or so. Now, if you look at participant 11, just for reference, you can see that their level 10 scratching is just about, maybe 75 milliwatts. And that's actually less than participant 3's number 1 level scratching. And that just shows how very different participants think of the subjective scale. So in terms of medical use cases of this technology, we believe it can enable continuous monitoring with little added effort from doctors and patients. In clinical and drug trials, the regressed power values can be used directly by researchers for quantitative and statistical analysis of treatment efficacy. And lastly, we believe this proposed power scale for scratch intensity holds physical meaning, allowing for future exploration of its relationship to skin damage. So we also did some scratch detection work, but for the sake of time, I'll speed past this. And we had participants do a variety of scratching activities and non-scratching activities. We then went ahead and trained some machine learning algorithms, and once again, we found the multimodal approach leads to superior classification accuracies in comparison to those single sensor approaches. In terms of key takeaways for this project, I showed you that multimodal sensing in a wearable ring form factors enables capturing features of scratching behavior. I presented a framework using a pressure-sensitive tablet to capture scratch intensity and train estimation algorithms. I showed that this provides patients and providers with a new quantitative metric that never existed before, specifically scratch intensity. And lastly, which we showed that this enabled the quantification of individual differences in interpreting those 0 to 10 scales used in clinical patient-reported assessments. I'd like to give a huge thanks to my co-authors for this project, especially Dr. Sonal Chowdhury, who's at UPMC. And this resulted in a publication in Nature Communications Medicine Journal. So now we're going to move on to project 2, which is on this gel site sensing probe for analysis of the skin surface. In this project, I'm going to show you how we can use 2 sensing modalities, specifically a camera and a load cell. We can integrate this into a portable device form factor, specifically a probe, and we can use this for tracking the skin surface topography, specifically for 3D reconstruction and also wrinkle depth estimation. The goal, once again, is to provide those quantitative measures for patients and their doctors that don't currently exist. So in the last project, we discussed tracking chronic itch in patients with using multimodal sensing. However, there are many more gaps for technology in dermatology. One huge gap is tracking skin texture over time. Skin texture is affected by many dermatological conditions. So for example, in eczema patients, increased scratching behaviors lead to the thickening of skin, which is called lichenification. And that means there's an increase in wrinkle depth. For patients with sun damage, that also increases wrinkles on their body. Skin texture is also affected by treatments such as moisturizers, creams, and medication. If we can track skin texture, we can likely diagnose conditions, track them over time, and thus treat them better. However, current solutions are very limited. They involve visual inspection or doctors touching the skin to feel it. And another example is single use case probes that just measure one data point at each location, such as the moisture of the skin. These probes are also typically very expensive. So the question we're really asking is, can we track these skin wrinkles using multimodal sensing? Before we hop into the technology, let's take a look at how deep wrinkles actually are. To measure wrinkles and other microstructures, we use a unit called microns, where 1,000 microns is equal to 1 millimeter. Wrinkles are specifically a few microns deep to hundreds of microns deep, based on the location of the body. And to put this into perspective, a sheet of paper is only about 70 to 180 microns thick. A human hair is only 20 to 180 microns in diameter, and a human red blood cell is just 7 microns across. So the question we really aim to solve is, how can we accurately measure these microstructures? And just as a little teaser, our reconstruction method achieves just about 12 micron error on wrinkles. So we specifically use a sensing method called gel site sensing. And here is an example of a gel site sensor. It consists of a camera facing an elastomer gel, which is simply a silicone material. Over here, you can see what it looks like when an object is pressed against the sensor. And specifically, this is a knuckle. The sensor also has 3 colored LEDs, red, green, and blue, which are pointing from different directions. This allows you to calibrate the sensor to get high-resolution 3D height maps from 2D images. Specifically, this involves mapping observed pixel RGB intensities to surface normals. However, calibrating the sensor for reconstructing the small skin-like features like wrinkles, both accurately and precisely, is challenging. This is because it requires collecting very accurate and precise calibration data and test objects to go ahead and assess if your method is working. It also requires soft gels that minimize deformation of the skin during contact with the sensor. So as part of this project, we go ahead and develop highly elastic gel cartridges that minimize the distortion during contact of the sensor with the skin. We go ahead and then present a learning-based 3D reconstruction algorithm for compact gel site sensors and evaluation on skin-like wrinkle test objects. And lastly, I conducted a human study with 15 participants to validate these algorithms, specifically quantifying wrinkle depth at various skin locations, and also assessing the impact of moisturization on skin wrinkle depth. So to start off with, we designed some custom sensing hardware. Our custom sensing hardware consists of highly elastic gels to minimize deformation of the skin during contact. We went ahead and characterized our gels using an Instron indentation testing machine with a spherical indenter and Hertzian contact theory. Our custom gels have a Young's modulus of about 130 kPa. For reference, the Young's modulus of skins ranges from tens of kPa to 3 megapascal. This means that we're likely not deforming skin that is more rigid, but we are likely deforming softer areas of skin. To ensure that the deformation is constant when taking multiple readings, we outfit the probe with a load cell to go ahead and keep the normal force consistent. In order to calibrate these sensors, we use a supervised learning approach to learn the relationship between gel site images and the surface normals. To do this, we need highly accurate and precise calibration data. We modify a 3D printer and use it as a 3-axis indenting rig. So in this picture, you can see this indenting rig with the gel site sensor mounted on the base plate and with an indenter mounted where the printer head would be. This allows us to automatically collect a variety of indentations with a spherical indenter, and then these can be labeled using a GUI to get our ground truth surface normal images. We use these gel site images and corresponding ground truth surface normals to train a convolutional neural net for predicting surface normals. We use a small CNN with a kernel size of 3 to prevent overfitting to spherical objects, and then we train it using a cosine similarity loss to basically find a loss between the predicted surface normals and those ground truth surface normals. During deployment, we can then go ahead and pass gel site images, which are skin images, through a convolutional neural net to get the predicted surface normals. From there, we use a Poisson integration solver to solve the differential equations to go from x and y gradients to a 3D height map. We also apply a deturning function, specifically a 2D high-pass filter, to remove low-frequency trends so we can focus on those higher frequency wrinkles. The skin image shown and this 3D height map are my fingerprint. In order to pick our best performing machine learning algorithm and to assess the ability of our algorithms to generalize, we 3D print a series of validation and test objects that resemble skin wrinkles. Our validation set consists of 4 straight channel pieces that are 500 microns wide and various depths. We press these objects against our gel to get our gel site image, and then we pass it through the deployment pipeline to go ahead and get our 3D height maps. To now assess if our method produces accurate height maps, we take several cross-sectional cuts across the height maps, shown by the green lines. An example cross-section is shown on the right. We can then pass this through a peak and valley finder to find the top and bottoms of each channels, and then this can be used to automatically estimate the channel height. And then we can go ahead and compare it to ground truth to get the error. We also have this test set, which consists of 4 circular channel objects that are 350 microns wide and at various depths that are different from the validation set. We collect metrics for both the validation and test objects using 2 different gels named Gel 1 and Gel 2. We then go ahead and run a series of hyperparameter searches and select the machine learning algorithm that yields the lowest mean absolute error for just Gel 1 on the validation objects only. So let's go ahead and take a look at some of those results. So first, I'm going to show you the results on the validation objects. So over here, we plot the predicted heights versus the ground truth heights for the 4 validation pieces averaged across the 2 gels. Using the R² value, which is coefficient of determination, and the ICC value, which is interclass correlation coefficient tests, we find a very strong correlation between the ground truth and the predictions. We achieve a mean absolute error of just about 14 microns across all the channels in the 4 validation objects. We see very similar performance on the test objects, achieving just around 12 micron error. Lastly, to assess the repeatability of our method, we plot the Gel 1 versus the Gel 2 predictions on this plot over here. And once again, you see very high R² and ICC values, which basically indicates that our method is both accurate and repeatable for these wrinkle-like channels. We can now go ahead and run a human studies with 15 participants to quantify wrinkle depth in 7 locations and show the effect of moisturizer on 3 locations. So first, let's take a look at some of those 7 locations. So this is what a fingerprint looks like in our gel site sensor. We can go ahead and then pass it through our deployment pipeline to reconstruct the height map in 3D. From there, we use some custom wrinkle detection algorithms, which identify the values in the 3D height map, and these are shown in blue. For the sake of time, I'm not going to go into huge detail on this algorithm. Using these blue lines, which are the detected valleys and surrounding peaks, we can go ahead and then sample a set of the valleys and get a distribution of wrinkle depths across this reconstructed surface. Using this histogram, we can then extract different wrinkle metrics. So in our case, we simply use the 80th percentile wrinkle depth value. So let's take a look at some of the other locations. So this is what the top of the finger looks like. And one thing to observe is how these histograms change in shape as the location changes. This shows the ability of our algorithms to detect variations in wrinkles across the body. So this is top of the finger, and now this is what the knuckle looks like. And as you may have noticed, there are more wrinkles at the higher depths. which is what you'd expect from from the knuckle area. This is what the top of the hand looks like. So shown on this slide are the 80th percentile wrinkle depths for the 7 locations across the body, across all 15 participants. And as seen, there are very distinct differences between each location, showing the ability of our device and algorithms to detect variations in wrinkle depth. So now I'll show you how moisturizer affects these wrinkles. And so this is what the palm looks like. So we have our gel site images, the reconstructed height map, the detected wrinkles, and once again, our histogram. We then go ahead and have the participant apply moisturizer on that location of the skin. We wait 8 minutes, and then we have them wipe it off with a wipe. And this is what it looks like after. So the gel site images, the reconstructed height map, and wrinkle detection look pretty similar. But then when you look at the wrinkle depth histogram, what you can see is a distribution shift trending towards lower wrinkle depths. And that makes sense because as moisturizer gets absorbed, the wrinkles become smaller in depth. We see the same trend on other locations, such as the wrist. And once again, you can see that distribution shift here. What we find is that moisturizer application leads to statistically significant reduction in wrinkle height for all 3 locations. So for each location, we take 2 readings in the same location before moisturizer application, and then we apply the moisturizer and take 1 reading after. If our sensor is both accurate and repeatable, we should see no difference between the 2 pre-readings, and we should see statistically significant differences in the post-reading versus the 2 pre-readings. And you can see that we find that for this plot for the palm, where NS stands for no significance and the asterisks indicate very strong statistical significance. We find the same trend for the wrist and also for the elbow. So in terms of key takeaways, I showed you that multimodal sensing in a portable form factor enables high-resolution 3D reconstruction of the skin surface. We showed that our probe can be used to accurately estimate wrinkle depth and to measure the effect of moisturizer on wrinkles. We showed that this provides patients and clinicians with a new quantitative measure that didn't exist before, specifically wrinkle depth. And lastly, this can enable future research in skin condition diagnosis and treatment monitoring. I'd like to give a huge thanks to all my co-authors, a lot of very talented people in a lot of domains, including material science, machine learning, various other fields. I'd like to also give a huge thanks to Dr. Arash Mostagimi and Dr. Sonal Chowdhury, who are at Brigham and Women's Hospital and UPMC, for giving me a lot of advice related to the medical aspects of this project. So now let's move on to the second part of this talk, where we'll focus on projects related to using multimodal sensing as interfaces for robotic caregivers. We focus specifically on individuals with motor impairments, as they stand to benefit most from this technology. Designing for individuals with severe motor impairments also sets a very high standard, increasing the likelihood that the technology can potentially extend to other chronic conditions. So the third project is going to be on this head-worn interface for control of mobile manipulators. In this part, I'm going to show you how you can use a sensing modality, specifically an inertial measurement unit, consisting of an accelerometer, a gyroscope, and a magnetometer. We can integrate this into a portable device form factor, something that is head-mounted, like a hat or glasses, and we can use this as a robotic interface for individuals with motor impairments, specifically for direct teleoperation or with shared controlled algorithms. The goal of this part is to provide personalized caregiving while maintaining the feeling of control and agency for the user. So in the United States, over 5 million people reported living with some form of paralysis, as shown in this figure from the Christopher and Dana Reeves Foundation. Paralysis and loss of motor function are most commonly caused by stroke, cerebral palsy, multiple sclerosis, and spinal cord injury. There are over 100,000 individuals living with these without the ability to use their hands due to cervical spinal cord injury. Caregiving robots are promising technology to enable individuals with motor impairments to once again do activities of daily living. Web-based interfaces are the current state of the art for interfaces for caregiving robots, allowing users to pick their assistive devices of preference to click on-screen buttons for control of robot motion. However, individuals with impairments, especially those without fine motor control, often have a difficult time accessing their computers easily and efficiently with their assistive devices. This can lead to long usage times for simple tasks, frustration, and discomfort. Novel assistive interfaces could lead to many compelling alternatives for individuals with motor impairments, improving personalized at-home care, that maintains the feeling of control for the user. Designing these robotic interfaces is an extremely involved process as it requires many design choices which often have trade-offs. These choices impact various qualitative and quantitative metrics that you collect from the users through evaluation studies. As an example trade-off, often you want to try to minimize workload for the user while using the interface. One way to do this is to increase the automation in the system, but this often leads to a decrease in the feeling of control for the user. These design choices and metrics affect whether the interface will be adopted by the target population. It is extremely important, once again, to design these systems in conjunction with both medical professionals and the end users themselves. So in this project, we designed a novel inertial sensing interface named HAT. HAT is this wearable direct teleoperation interface, requiring only head motion that is often retained after spinal cord injury. The interface consists of an off-the-shelf absolute inertial measurement unit, which fuses accelerometer, gyroscope, and magnetometer data and outputs absolute roll, pitch, and yaw angles. These orientation angles are used to control actuators on the mobile manipulator. So this project consisted of two parts, and for the sake of time, I'll speed past the first part, which consisted of early exploration with HAT, and I'll focus on the second part. So in the first part of the project, we introduced this novel assistive interface. We showed how it enabled teleoperation of a mobile manipulator, and then we went ahead and evaluated it with 16 participants without impairments and 2 participants with motor impairments, and we showed the interface enabled participants to complete various tasks with low error rates, high perceived ease of use, and low workload measures. However, one of the main limitations of this project was the lack of long-term testing in the home with an individual with severe motor impairments. So after publishing an initial paper on this work, we aimed to tackle these limitations, and we iterated on the interface over the course of the year with input from Henry and his wife, Jane. We then traveled to California to test HAT for a week with Henry and his wife in their home. Henry is an expert robot user and has participated in many studies. He's an individual with quadriplegia due to brainstem stroke. So in the second part of the work, we evaluated HAT through a week-long case study with Henry Evans in his home environment. We introduced driver assistance, a form of shared control, to reduce task times and errors during grasping tasks. And lastly, we demonstrated the customizability and generalizability of the interface. So our system includes HAT and a clicker that allows Henry, a non-speaking individual, to mode switch. For the HAT hardware, we attach all electronics to a foam piece with Velcro, which allows HAT to be attached to any head covering of the user's preference. Henry preferred using this chin strap shown on the left, which is typically used for stopping snoring. The robot we used for this project was the Hello Robot Stretch. Orientation angles from the head-worn interface are communicated to the robot and mapped to velocity commands for the robot's actuators based on the mode. There are 4 modes: drive, arm, wrist, and idle. The velocity command sent to each actuator is calculated using a piecewise function, which takes into account the angle of the user's head and the initial position of the HAT. The farther the user tilts their head from this calibrated position past the lower threshold, the faster the robot moves. So let's take a look at the arm mode mapping. Pitching your head up moves the robot's arm up, while pitching your head down moves the robot's arm down. Turning your head to the right extends the arm, while turning your head to the left retracts the arm. So as you can see, it's a pretty intuitive mapping where the robot directly mimics your head motions. We introduced driver assistance, which is a shared control algorithm for mobile manipulators. So what is shared control? Shared control is when user input from control interfaces is combined with the robot's autonomy to reduce workload. However, often when shared controlled algorithms are introduced, it leads to loss of feeling of control reported by the users. We aim to address this with our algorithm. So our system works as follows. The RGB and depth images are fed to our perception system, consisting of an open vocabulary perception model, which outputs possible goals. From there, our intent recognition module chooses the most probable goal by computing the distance between the robot's end effector and the possible goals. From there, a controller then outputs the robot's assistance. That is lastly combined with the human input to produce the blended control output. The video on the right shows the full grasping sequence of a Red Bull grasping task with driver assistance. The video on the left shows just the segment where driver assistance aligns the robot's gripper with the Red Bull can. As shown, when driver assistance is turned on by Henry, we prevent the robot from controlling the arm extension, the base translation, and the wrist rotation, so that it is only facilitating alignment with the object. This allows the user to remain in control of how the robot approaches and grasps the object with the arm. We also added this graphical user interface to the system with camera feeds from the robot to allow users to control the robot out of line of sight. In this video, Henry uses this GUI to manipulate the blinds. We also show that HAT is a flexible assistive interface that can be used for controlling the cursor of a computer. In this video, Henry uses HAT's cursor control to search for a video on YouTube. Let's take a look at the week-long study schedule with Henry. First, we have some instructional phases, and then we repeat one task, blanket tissue trash, each day to track learning curve of the interface over time. We also do a set of other predefined tasks on days 1, 2, and 3, and additionally on day 7 to track progress. Some of these tasks are done with the GUI. We test out cursor control 4 times during the study. On day 5, we also do 3 tasks with and without driver assistance to evaluate the performance of the system. Lastly, on day 6, we have an open day of tasks where Henry performed 4 additional household tasks of his choosing with the interface. The repeated blanket tissue trash task is shown on the left. On the right, a clear downward trend is shown over the course of the week in task completion times and resets of the environment. A similar trend is seen with the rest of the predefined tasks conducted at the start and end of the study. We track several 7-point Likert items pertaining to ease of use, errors, error recovery, time, and preference for HAT over a comparable direct teleoperation web interface. A higher score is better for all items. Henry gave positive scores for all the items with his highest ratings on day 7. We additionally track workload using a 7-point NASA TLX scale, where lower scores are better for all items. On day 7, Henry ranked workload low across all categories. On the left is a video of our driver assistance system in action compared with direct teleoperation. We find reductions in task completion time while using driver assistance for all 3 tasks, while maintaining the feeling of control for the user. On the right, we find that driver assistance significantly reduces workload measures for grasping tasks. Henry had strong praise for the system, saying, "That's better than anything I've tried for grasping." And that means a lot as he's been testing these caregiving robots for over a decade in his home. We believe that customization of interfaces is very important to allow individuals to interface efficiently and comfortably with the mobile manipulator. Without customization, Henry would not have been able to use HAT. HAT allows this customization in a few ways. First of all, switchable axes allows the user to select any 2 of the roll, pitch, and yaw axes for robot control based on their preference. In Henry's case, he used the pitch and yaw axes as he has limited mobility in his roll axis. Secondly, plug-and-play mode switching allows for a range of inputs, such as Henry's clicker or speech recognition. Lastly, the physical design is personalizable, meaning that the HAT hardware can easily be swapped in and out of any head-worn garment. There are many insights we derive from our work with HAT. In conclusion, I'd like to specifically highlight some of the pros of wearable interfaces in comparison to web interfaces, which is the state of the art for mobile manipulators. Web interfaces are great as they have a greater number of inputs through on-screen buttons, they have camera feeds, and they allow for the simple activation of autonomous routines. Wearable interfaces, on the other hand, are always readily accessible when needed and inconspicuous when not in use. They can offer a more direct and intuitive means of controlling mobile manipulators. And lastly, they provide increased flexibility while conducting tasks around the body. So you can see in this feeding task, Henry is fully free for the feeding with no kind of screen in front of his face during the feeding motions. So in terms of key takeaways, I showed that multimodal sensing in a head-worn form factor can be used for direct control of an assistive mobile manipulator. We showed that HAT is efficient, easy to use, intuitive, and low workload through long-term testing in the home. Lastly, we showed our driver assistance shared control algorithm can further reduce workload while maintaining the feeling of control for the user. This work resulted in 2 publications, one at ICRA 2023 and one at HRI 2024, where it won a Best Paper Award. I'd like to give a huge thanks to all my co-authors for both these papers. These are the co-authors from the second paper, especially V. Nguyen, who's an occupational therapist who works with Henry and Jane and gave us a lot of insight on how to run a study in the home, and also Henry and Jane Evans, who welcomed us into their home for a week. We stayed with them and had a great time running the robot and having Henry test out all the different technology we created. So lastly, I'm going to move on to project 4, which is a wearable interface for bite timing estimation. In this project, I'm going to show you how you can use 2 sensing modalities, an IMU and a contact microphone. We can integrate this into portable device form factors, specifically smart glasses and a throat microphone. And we can use this for bite timing estimation for individuals with severe motor impairments during robot-assisted feeding. Again, our goal here is to provide personalized caregiving while maintaining the feeling of control and agency for the user. So previously with HAT, we initially tested it as a direct teleoperation interface. This is also known as active control, when the user's intentional actions or movements directly trigger robotic movements. Through shared control, we then try to reduce workload while maintaining the feeling of control for the user. One of the goals with interfaces should be to further reduce workload and task times while still making sure the feeling of control stays as high as possible. Towards this goal, I want to explore a new type of interface that we term passive control. Passive control is when the robot uses non-intentional or subtle human signals to initiate or modify its actions. Passive control could be a method of further reducing workload while still maintaining benefits of active control, such as the feeling of control for the user. We explore passive control through the problem of bite timing estimation in robot-assisted feeding. Bite timing is when a robot should feed a human the next bite of food. Bite timing is an extremely challenging problem, as we found, as it is a very subconscious feeling. If you think about when you eat food, you don't think about when to feed yourself. You just do it at the correct time. Because of this, bite timing varies drastically based on the participant, the setting, and other variables. It is also very challenging as there are often many correct timings that users will accept. Past work in bite timing is very limited as a result. One project is shown on this slide. However, the problem with their system is it is very constrained, as it requires a camera and microphone array positioned at the center of the dining table. It can also only be used for social dining with 2 accompanying diners, and it was also not tested with individuals with impairments. This limits its ability to be deployed into real world and into many realistic settings. So in this project, we aim to solve bite timing using a multimodal wearable system. First, we introduced this system consisting of an IMU on smart glasses and a throat microphone, and we collected a bite timing dataset from 14 participants. From there, we trained a novel reactive bite timing algorithm that generalizes across users, feeding robots, robot positioning, foods, and individual and social dining scenarios. Lastly, we evaluate our algorithm through 2 evaluation studies with 15 participants without impairments using the OBI robot and 1 participant with impairments using the Feast robot system. So as part of this project, we ran 3 different human studies named Phase 1, Phase 2, and Phase 3. So I'll start with a little bit of an overview of these studies. Phase 1 was a data collection study with 14 participants with no motor impairments. We used the OBI feeding robot positioned in front of the user, feeding from the front. We used an assorted set of foods and collected data for both individual and social dining scenarios. Phase 2 and Phase 3 were both evaluation studies with individuals with and without motor impairments. As you can see from the table below, we switch up the type of robot we use, the positioning, the feeding trajectory, and the foods across all 3 studies to show the ability of our algorithms to generalize to various conditions. So first, I'll show you the Phase 1 data collection study. In this video, you'll see the camera footage from the robot, and then the 3-axis accelerations on the top right from the IMU on the glasses, and the throat microphone data on the bottom. For this study, the robot is controlled by the participant for half the studies and by the researcher for the other half of the studies through a Wizard of Oz scheme to gather accurate bite timing training data in 2 different scenarios. One where the user is controlling the robot themselves, and the other that kind of mimics more like a caregiver getting the bite timing right. This also allows us to capture errors in bite timing made by the caregiver, who in this case was a researcher doing the controlling of the robot. Let me show you how the pipeline works. So we have our participant here with our throat mic and IMU on the glasses. We then use 1-second samples of this IMU and throat mic data. And what you can see here is various examples of different motions and the data during robot-assisted feeding. From there, we can take our hand-picked features from the throat microphone and IMU data, and we can concatenate these. We then use this to train a simple bite timing algorithm that learns the general trends between the motion data and the time until the next bite. To then deploy the system to our robot and enable the reactive behavior that we want, we use a simple thresholding method, which we call assertiveness thresholding. As part of this, the user selects an assertiveness threshold, and we use a simple if-then statement with the predictive time till next bite to go ahead and choose whether to progress the robot or to stop it in its place. This process allows the user to have some control of how assertive the robot is during deployment, where lower thresholds result in more cautious behavior, while higher thresholds produce more assertive feeding actions. So this video shows our deployed pipeline in action, and what you're going to see is the IMU signals on the top right again, the throat mic in the middle, and then the line at the bottom is basically the predicted time in seconds, with the horizontal line indicating the assertiveness threshold. On the left, you're going to see the participant in the video, the binary command of starting and stopping the robot, and then the predictions in seconds. And what you'll see is that the predictions are high when the user is kind of talking and moving, and then they drop down when they stop. And that enables our robot to start and stop along the trajectory. Using our phase 1 data, we can get some baseline metrics on how well our approach will work. So first, we present the mean absolute error of our bite timing regression model. We find that the multimodal approach leads to the lowest error. We can also calculate various binary metrics, such as accuracy and NMCC score, after the assertiveness thresholding. These should be considered as alignment performance metrics, specifically how aligned our algorithms proceed and stop commands were with the commands provided by the participants. We once again find that the multimodal approach works the best, performing significantly better than the policy that always feeds the user. Now we can go ahead and run our phase 2 study evaluating against 2 baselines, fixed interval and mouth open. Yeah.
What's the ground truth there?
The ground truth is the user, like they press start and stop button. And so one thing to just note here is that that's why I called it alignment metrics, because their previous actions influence the future actions. So we just see how aligned our thresholding method was. Yeah. So first we'll start with the fixed interval method. And this is a video from our study, specifically social dining. And so this method basically waits 45 seconds between each bite. And because of this, it can be considered a fully autonomous method as no user input is needed. So in this first part of the video, it's at 8x speed. We speed past the 45 seconds. The second part is at 2x speed. And what you'll notice is that the robot fed the user while they were still talking, which is the wrong time. This next method is the mouth open method during social dining. This requires the user to turn and face the camera on the robot and open their mouth. This can be considered an active control method, as it requires the user to make an intentional action to trigger the robot's movements. So what you're going to see here is the user is talking, then they want a bite of food, they turn, open their mouth, and then the robot progresses. And once again, it didn't feed the user at the right moment because they started talking again. Now let's take a look at our wearables method. In this method, the user can act almost fully naturally, and this is a form of passive control because they're kind of subtle human movements directly trigger the robot's movements. And so this is at normal speed. The participant is talking in the beginning. The robot kind of stays still, maybe nudges forward a bit. Once they stop talking and the researcher is actually talking at that point, the robot then decides to go ahead and make the full progression to feed the user. And that was the right timing as the user was not talking or chewing at that point. So we had the 15 participants blindly rank the 3 methods for social dining. And we find that the wearables was preferred by most participants, receiving 67% of first place votes. One participant explained their preference for our method, saying, "I think the wearable method was especially beneficial for the social setting, since the actions for pausing the feeding align well with the social cues where I'd rather not be disrupted." Participants also answered various liquor items related to their experience. There are a few I'd like to specifically highlight, which we found were extremely interesting. The first is the feeling of control, where the wearables method directly matched the mouth open method, which is extremely interesting because, as a reminder, the mouth open method required directly triggering the robot motions as it is an active control method. In comparison, the wearables method can be considered almost fully autonomous and is what we coin passive sensing. We find the same thing with robot understanding, where participants actually felt that the robot understood them better while using the wearables method, slightly more than the mouth open method, and a lot more than the fixed interval method. Now, if we look at mental and physical workload, we find that the wearables method directly matches the fixed interval method, which was considered the autonomous method. And this is a great sign, as it shows our passive sensing method matches the low workload of the fully autonomous method while matching the feeling of control of the active control method. And this is really exciting because in most past papers on work that introduce autonomy, you often find that it drastically reduces the feeling of control for the user. And what we've shown here is we've drastically increased autonomy and we've still maintained the feeling of control. So now let's take a look at individual dining. And what you'll see here is when the participant finishes up chewing, the robot then decides to go ahead and feed them at the next bite of food. And this typically aligns with when participants want the next bite when they're wrapping up their chewing behaviors. For individual dining, we find that participants even more strongly preferred the wearables method over social dining, with 87% of participants ranking it the first choice. One participant said, "I like the wearables timing the best because it didn't force me to wait for another bite like the other ones. It kind of naturally matches my pace. The other ones felt a little slow or fast at times." We found the exact same results for the liquor items related to individual dining. So once again, our passive sensing method matches the low workload of the fully autonomous method while matching the feeling of control of the active control method. In terms of overall rankings, we find that the majority of participants preferred the wearables method. Lastly, our collaborators at Cornell ran our phase 3 study with a single individual with motor impairments. For this study, we completely changed our study setup. We used a completely different robot system, the Feast system, which consists of a 7-degree of freedom Kinova robot arm. The system is able to autonomously acquire food and detect where the participant's mouth is. So in this video, you can see that the robot grabbed a slice of banana automatically. It then goes ahead and detects where the participant's mouth is, and then uses our wearable system to go ahead and decide bite timing. What you'll see here is when the participant starts talking, the robot's going to pause in the middle of the feeding trajectory and then continue once they stop talking. So the participant only tried out this wearables method, and they gave it very strong praise, saying it is close, no difference between a caregiver and a robot. We plan to run further studies with more participants in the upcoming months. In terms of key takeaways, we found that multimodal sensing in a wearable form factor can be used for accurate bite timing estimation in robot-assisted feeding. This approach can generalize to both individual and social dining scenarios, multiple robots, multiple robot positioning, many foods, and to various users. Lastly, we showed that passive sensing paradigms for robot control can further reduce workload while maintaining the feeling of control for the user. I'd like to give a huge thanks to all my collaborators for this project, especially the team at Cornell that helped with running those studies in Syracuse. So in this talk, I presented 4 projects related to multimodal sensing for dermatological conditions and multimodal interfaces for physically assistive robots. These projects were towards the goal of providing quantitative measures for patients and their doctors, and for providing personalized caregiving while maintaining the feeling of control and agency for the user. Together, these efforts move us closer to a future where chronic care is data-driven, continuous, personalized, and empowering for those who need it the most.